In this video, we would like to start learning how to conduct a hypothesis test for the population mean. To get us started, we need to conduct a quick initial review of the student's t distribution with n-1 degrees of freedom. To illustrate how this is done, we take the following example and complete parts A through C below. In part A, we are to determine the critical value of values for a right-tailed test for a population mean at alpha equals 0.10 level of significance with 20 degrees of freedom. So in this case, I am told this is a right-tailed test, and since I'm dealing with the t distribution, you recall that the t distribution looks like the normal distribution, except that it has heavier tails. All right, with that said, I'm going to take this off the picture. And to get the critical value for a right tail test, it means I'm only going to put this on the right tail. So I'm going to shade the rejection region, and I need to find the critical value using the t distribution with n-1 degrees of freedom. So my degrees of freedom, I'll just write df is always n-1. In this question, I've been told the final answer. It is 20. So that means my sample size must have been 21. So that 21 minus 1 is 20. So how do I check this in the t distribution? To check my critical value, I need the size of my rejection region, and that is always alpha. So alpha equals 0.10. So this is 10%. Okay, so with that said, we can go to StatCrunch. I'll go to Stat, Calculators, go to the t distribution, and I'm going to drag this a little bit to the center. And in particular, I want my DF, my degree of freedom. DF is, degree of freedom is 20. So I'm going to set that in. So I'm going to change this to 20. The next thing I want is, this is an area to the right. So this is right-tailed. This is greater than. So let me set the right arrowhead, greater than. Then what is the size of that area that is greater than? Going back, that is my alpha, which is all concentrated in the right tail. That's 10%. So I'm going to set that value. So 0.10 and compute. So my answer is 1.325. That is my critical value here for the t distribution, 1.325. Question B. I would like to determine the critical value for a left tail test. So again, sketch my t distribution, this time a left-tailed test. Okay, and at the alpha equals 0.10 level of significance, that is the size of this area that is shaded on the left, based on a sample size of n equals 10. This time, I am not given the degrees of freedom. Degrees of freedom is usually n-1. So my n here is 10 minus 1, which is 9. So I'm ready to go back to StatCrunch. And this time, I want my degree of freedom to be 9 based on my computation. And I want it to be on the left, which is less than. Okay, so I am going to choose less than this time. I'm going to erase this because I want to key in the size of the area here, 0.10. So 0.10 on the left, the cutoff point is negative 1.383. So my critical value here for this left tail test is negative 1.383. We proceed to question C. Determine the critical value of values for a two-tailed test. So for a two-tailed test, I'm going to draw my two tails. Then notice that in this case of the two-tailed test, my alpha is equal to 0.05. So this means that both of these guys should add up to 5%. So each person will take an even split, 2.5%. So 0.05 divided by 2, 0.025 goes here, and 0.025 goes here. Okay, well, if I don't want to stress that much, one thing to notice, if 5% are both in the shaded lower and upper tails, it means the remaining 95% is between this case. And I can use that immediately to find my two critical values here, which one is going to be negative, the other one is going to be positive. So an easier way would probably, in this case, would be to go the between way. What do I mean? I will click on between. I will set my degree of freedom. What is my degree of freedom in this case? My degree of freedom is based on my sample size. It is n minus 1. That will be 17 minus 1, which is 16. So you have 16 in this case. And then I would like to indicate that the amount of probability between is 0.95 and compute. So for between, the size of what is between is 0.95. So I have negative 2.1199 to positive negative 2.1199 to positive 2.1199. So my critical values are plus or minus 2.1199. So with that set, we're ready to begin a formal test on the population mean. Here we have been given the null and the alternative hypothesis. We have given the sample size obtained from a population that is known to be normally distributed. To complete part A, we're told that if the researcher decides to test this hypothesis at alpha equals 0.1 level of significance, determine the critical values or values. So in this case, if we look at this, how many tail tests do we have? This is a single left tail test. So I can use technology or the t-distribution table to find the critical value. So let's proceed to do that. I'm going to sketch my t-distribution, and in which case I will follow up with how many tails. This is a left-tailed test quickly, and then the next step will be to find the critical value using the t-distribution. The t-distribution will require n minus 1 degrees of freedom. My n is 22, so 22 minus 1 is 21, and the size of my alpha here is 0.1, which means I have 0.9 here. So to find my critical value, in this case, I'll go to Start Crunch. I'll change this to standard since I only want that. Then I want my degree of freedom to be 21. So I have this to be 21. And the next step will be, where is the whole area concentrated? Going back, the whole area is concentrated to the left. So I want to make sure this is left. I'm going to delete this. And I'm going to key in the size of the area to the left. The area to the left is 0.1. So I have 0.1 and compute that. So you have negative 1.323. That is my critical value. Then, for question B, I am to compute the test statistic. To compute the test statistic, I will note that my x bar is the sample mean, and my lowercase s is the sample standard deviation. This I will take to StatCrunch using the t-stats calculator to get the test statistic. So let's go and do that. I will go to StatCrunch, go to Stat. This time, go to t-stats, one sample with summary. And you'll be asked to input the value of the sample mean. The sample mean in this case is x bar, which is 37.8. So 37.8. And then the sample standard deviation is 14.1. So I'm going to key in 14.1. And the sample size is our n. N is equal to 22. So I'll key that into And for the hypothesis test, we need to look at the hypothesized value of the mean, 40, 40. So you have 40 and less than 40. So I'm going to do that. So I have 40 and less than 40. Make sure you set this up appropriately, then compute. And from here, we have the t-stat, which is negative 0.7318. That is our critical value. Sorry, that is our test statistic, rather. So at this point, now that we have the test statistic, we need to figure out where this lies. Is it in the shaded rejection region? What do you think? This is negative 0.7. This should come before. So which means it does not fall in the rejection region. So will the researcher reject the null hypothesis? Well, since your test statistic does not fall in the rejection region, we will not reject the null hypothesis. In other words, the researcher will not reject the null hypothesis. So the answer to this question is no. So as observed, since the test statistic of negative 0.7318 does not fall in the rejection region, we do not reject the null hypothesis. With that done, we have completed this question. We now go on to the next example. For the next example, we are told that a college entrance exam company determined that a score of 24 on the mathematics portion of the exam suggests that a student is ready for college level mathematics. To achieve this goal, the company recommends that students take a core curriculum of math courses in high school. Suppose a random sample of n equals 150 students who completed this core set of courses results in a mean, so sample mean, a mean math score of 24.8 with a sample standard deviation S of 3.8. Does this result suggest that students who complete the core curriculum are ready for college level mathematics? That is, are they scoring above 24 on the math portion of the exam? This is the question that we want to test. So we are ready to state the null and the alternative hypothesis. We're interested in if the mean is above 24. That is what we want to test. Is it greater than 24 versus the alternative or versus the null hypothesis that it is set at 24? So with that said, we can proceed. We can proceed to the next part of the question, which is to verify the requirements to perform the test using the t-distribution. These requirements are as follows. There are three of them, 1, 2, and 3. The first one is that the sample size must be larger than 30. The second one is that the students' test scores must be independent of one another. They must not be dependent at all. Then the third requirement is that the students were randomly sampled or chosen. With that done, we proceed to the next part. Use the classical approach at alpha equals 0.10 level of significance to find the critical value and test the hypothesis. Identify the test statistic. In order to use the critical value and the test statistic, step 1, we find the critical value. So for the critical value, that's the first thing. I'm going to draw my sketch my t-distribution in this case. And I will notice that this is a one-tailed test. Since a one-tailed test is in the direction of the right, so I'll put the rejection region on the right, and I need to find the critical value in this case. What is that critical value going to be equal to? Well, since I'm using the t-distribution, I do need the degree of freedom, which is n minus 1. And so that will be, what is my n in this case? My sample size is 150. So let's see. So 150 minus 1 is 149. And I would like to note that what is the size of this area on the right here? That is always my alpha. So this is alpha equals 0.10. So I can take this to StatCrunch to my T calculator. So start, go to my calculators, go to the T calculator, and I want to key in my degree of freedom. The degree of freedom is 149, so 149. And then next, the region is to the right, which means greater than. So I want to set this to greater than. I'm going to remove this. And what area is greater than? What is the size of the area? The size of that area is your alpha, which is 0.10. So this is 0.10, and I will compute it. The value is 1.2873. So my critical value is 1.2873 to 4 decimal places if I want. And then the next thing is to find the test statistic. So what is my test statistic? I need my X bar, the sample mean. The sample mean was 24.8. I need my sample standard deviation, which was 3.8. And I need my sample size, which is 150. I'll take all of these quantities to StatCrunch. So close this. I'm going to go to StatCrunch, go to T-stats, one sample with summary, and I'm going to key in the sample mean, the sample standard deviation, and all of these parameters. So right here on my screen, I have all the sample mean, the standard deviation, and the sample size from my working bench, which I got earlier from the question. And the next thing I need to note is what the hypothesized value of the mean is, which is 24, and the alternative is strictly greater than 24. So I will go here, I'll set this to 24, and then this is greater than 24. And I will compute. So I have my calculated value here, my test statistic here, which is 2.5784. So now that I have my test statistic 2.5784, I will map it onto this diagram. Where does it fall? What you might observe immediately is that this falls right above 1.2873. Remember, the critical value of 1.2873 is here. So 2.5 should be somewhere ahead. What is of interest to me is that it falls in the rejection region. So I can write a conclusion then here. So since the test statistic of 2.5784 falls in the rejection region, as we saw earlier, we're going to reject the null hypothesis, which means going back. This is the bad one. And what we want to test has sufficient evidence for it. So I'll conclude that there is sufficient evidence to indicate that the mean is greater than 24, or what it means in the context is that the students are scoring above 24. We now proceed to the next example. In this example, we are told that the mean waiting time at the drive-thru of a fast food restaurant from the time an order is placed to the time an order is received is 87.8 seconds. A manager devises a new drive-thru system that he believes will decrease wait time. As a test, he initiates the new system at his restaurant and measures the wait time for 10 randomly selected orders. The wait times are provided in the table to the right. Well, we will have that in our own chapter 10 data sets. Complete parts A and B below. So, part A, because the sample size is small, the manager must verify that the wait time is normally distributed and the sample does not contain any outliers. The normal probability is shown below. We will output that ourselves, and the sample correlation coefficient is known to be 0.989. Are the conditions for testing the hypothesis satisfied? Let us see where the data set is. To see where your data set is, you'll be able to see in the same folder that holds your printable lesson notes, the chapter 10 data sets. So you can go ahead and click on that data set, and then there should be an automatic download. So here on my screen is the data set, and although I called it page 19 data set, but that was adjusted later. So in particular, going back to my work notes, the goal is to check if the wait time is normally distributed. What does that entail? To answer that question, I'm going to get the normal probability plot first. So again, I'm going to get the normal probability plot first in StatCrunch. So going back to StatCrunch, I have the data set already here, and I will go to graph. I want a QQ plot, which is the normal probability plot. So I want the data stored under variable 1. So I'll choose this, and I will like the normal quantile on y-axis. So I will compute that. And as you can see, there is no crazy departure of the points from the red line. As long as those points are not crazy far away from the red line, we can conclude that this data can come from a normally distributed population. So that satisfies that first requirement, that the sample size, even though it is small, should come from a normally distributed population. Then to check that it does not contain any outliers, all I need to do is draw, again, a box plot of the variable. And in this case, I would like to draw the boxes horizontally. So compute, I can see that there are no stars to indicate that there are any outliers. So again, that condition is met. And again, we would need to also check if comparing the sample correlation coefficient to the critical value for testing this type of, for testing hypothesis on the correlation coefficient, if it is greater. So in this case, what do I have? I have my R, the correlation coefficient, 0.989, and I need to find the critical value for n equals 10 when testing hypothesis on the correlation coefficient. Where do I get that value from? Going back, I have a similar question here, and I can click on this icon. When n is equal to 10, the critical value is 0.918 rather. So taking that back here, the critical value is 0.918. Since the correlation coefficient is greater than this value, then it tells me that all conditions for testing the hypothesis has been satisfied. So to reverse or to remind you of that, 1, this condition is met. The correlation coefficient is greater than the critical value. Then 2, the normal probability plot shows points that are linear enough, and then 3, box plot shows no outliers, These 3 conditions guarantee that I can still conduct a hypothesis test even though my sample size is small. Then the next thing is, to conduct the hypothesis proper, I need to answer the question, is the new system effective? That means, first of all, I'm going to split this into 2. I need to set up my null and alternative hypothesis based on the context of the problem. Remember that initially, the guesstimate is that it is 87.8 seconds. Well, this manager would like to check if it has what? If it has become effective. That means has it decreased compared to what it used to be. So we want to see if the mean wait time has decreased from 87.8. So the null will be, it is still at 87.8. So again, we need to find, that is step 1. Step 2, as usual, we need to find our critical value. I'll sketch my t-distribution, and the alternative hypothesis says that this is a left tail, one tail test. So I'm going to locate my rejection region, and that is my RR. The size of my rejection region is my alpha, which is 10%, leaving the remaining 90% here. And so I'm ready to find my critical value. But since I'm using my t distribution, I need my n minus 1, which is my degrees of freedom. And n in this case is my sample size. 10 randomly selected values with randomly selected orders. So df is equal to 9. Take note, I got my n equals 10 from the question. The question said that they selected 10 randomly selected orders. So that is the sample size. So I'll take this back to our start crunch. I'm going to close this and close this. And I'm going to go to calculators, go to my t distribution. Okay, this is acting weird. Let's see. So you have the t distribution, and I would like to drag this aside. My degree of freedom is 9, and going back to my work, this is 9, and on the left, less than, I want 0.1 there. So on the left, less than or equal to, I'm going to delete this, and I want 0.1, and compute. This is negative 1.383 again. So I have my critical value there, negative 1.383. Then the third step would be to find my test statistic. My test statistic will require the sample mean. What was the sample mean of X bar? From this case, you will observe that the sample mean was not given. And that makes sense because we already have the data itself, the raw data itself. So I'm going to just exit this, go to stats, and indicate that I want to do a t-stats, one sample, no longer with summary. This time I have the raw data, so with data. And I'll choose variable 1. So variable 1, that's what I want. And I want to perform a hypothesis test, and the mean, the hypothesized value of the mean, let's go back, is 87.8 versus less than that value. So 87.8 versus less than that value. And that is all I need in this case. So go ahead and compute. So let me drag this up, and I have my t-stats here, which is my test statistic. So this is negative 1.9458. So my test statistic is, I don't need this, I already have the data, is negative 1.9458, I believe. Let's check that. Negative 1.9458, yes. Okay, then with that said, we can proceed. Now that I have my test statistic, which is negative 1.9498, this should be somewhere to the left, 9458, which means it lies in the rejection region. So since the test statistic of negative 1.9458 falls to the left of negative 1.383 in the rejection region, we're going to reject the null hypothesis and conclude that since we're rejecting the null hypothesis, we have sufficient evidence in favor of the claim that the mean is now lesser than 87.8 seconds. In the context of this problem, that means we now have sufficient evidence to indicate that the new system is effective since it has lowered the mean waiting time from the previous 87.8 seconds. So this brings us to the end of the consideration of constructing confidence intervals for population mean.